What if the first genesis of life, the abiogenesis, is so unlikely that it only happened once in the entire galaxy, and that once was not on Earth? What if primitive life arrived on Earth after having travelled vast distances across the Milky Way? Some scientists think this may be the case. This is the Panspermia hypothesis. There's something odd about the first appearance of life on Earth. The oldest fossils are now dated to only a few 100 million years after the moment Earth first became habitable. Is it really reasonable to imagine that evolution turned an unliving chemical soup into the first true living cells in that geological eye blink? Well, maybe, but it's also possible that life on Earth didn't start on Earth at all. Perhaps it started on a distant world somewhere in the Milky Way and somehow survived a long journey through the void to colonize the early Earth. The plausibility of panspermia comes down to whether or not any living organism can survive its three deadly stages: ejection from an origin world, travel to the new world, and entry to that world's biosphere. Let's start with the exciting parts, the beginning and the end of the journey. One way for a budding microbial astronaut to travel the stars is via lithopanspermia, basically be attached to a rock that travels between planets. Now, we know that debris from planetary surfaces can be ejected into space during asteroid or comet impacts. Hundreds of meteorites have been found on Earth that have compositions suggesting they originated from the Moon or Mars. Many chunks of Earth have also been ejected into space, most of them from the largest impacts like the one that killed the dinosaurs. Some of that debris would have contained life, but could hitchhiking microbes have survived that ejection? To escape Earth's gravitational field, a chunk of impact debris has to be kicked to a minimum of 11.2 kilometers per second. That's the escape velocity at Earth's surface. That requires an acceleration of up to hundreds of thousands of Gs and hundreds of thousands of Earth atmospheres in shock pressure. Similar forces apply when it smacks down at the other end of the journey. Temperatures in these rocks can rise to several hundred Kelvin in the impacts and during re-entry. That all sounds pretty unsurvivable, but scientists have engaged in various forms of microbe abuse to test this. This includes shooting high-velocity projectiles loaded with colonies, spinning them up in an ultracentrifuge, attempting to splat colonies with extreme pressure impact plates, and if that's not realistic enough, microbe-laced rocks have been dropped from space, strapped to the outside of re-entry vehicles. Many life forms have been tested, from common bacteria that you find everywhere in the soil, to primitive cyanobacteria, to heat-resistant extremophiles, and even fungus spores and lichens. While survival rates may be low, at least a small fraction of bugs of any of these types can survive the pummeling of high-pressure acceleration. Exposure to extreme temperature, for example in atmospheric re-entry, is more problematic. Some extremophiles can survive at temperatures above 100 Celsius, but the surfaces of rocks during impact or re-entry will be much hotter than this. And this is where we identify our first microbial contender for panspermia: endoliths. These are organisms that live deep within rocks, deep enough that they're protected from the extremes of temperature change. As we'll see, endoliths are exceptional candidates as microcosmonauts for a number of reasons. They may also be the only critters that can actually survive the journey between planets. But before we talk about the hazards of that journey, let's look at a gentler mechanism for getting life into space. A wide variety of living single-celled organisms are found floating around in the atmosphere, as high as the stratosphere. Some of this material may make it into space. Just this year, Russian cosmonauts reported the discovery of familiar bacterial DNA on the outer surface of the International Space Station. They suggest it rode electrical currents from the atmosphere below, or it came from space. Probably the former though. These levitating microbes have a gentler journey up, and they may also have a faster trip to their destination. Very small individual bacteria can be accelerated by their star's own radiation and be ejected from the solar system. This is radiopanspermia. Stars may be constantly spraying their germy life through the galaxy. In some respects, it sounds like levitating into space and becoming your own solar sail is way more efficient than lithopanspermia. Except for one thing. The vicious environment of space probably annihilates all microbes not surrounded by a nice big spaceship made of rock. Getting up and down again from space is the fun part. But for a budding panspermial life form, the journey itself is simultaneously the most boring and the most lethal. Our pilgrim microbes have to contend with near absolute zero temperatures, extreme dryness, a hard vacuum, and probably worst of all, some incredibly destructive radiation for up to millions of years. So can they do it? The best way to simulate the conditions of space travel is to send things to space. The first experiment was way back in 1936 when fungal spores were sent on a stratospheric balloon ride. Since then, every potential panspermiating life form has taken rides on various satellites, most notably the International Space Station. It's mostly single-celled organisms and spores, but also tardigrades and nematodes. Some of these tests were actually to test survivability on Mars, but the results translate, and in some, the results are clear. Many bugs can survive the vacuum, freezing cold, microgravity, and absolute dryness of space. But radiation is a problem. We'll come back to that. When protected from radiation, various bacteria, fungi, lichens, archaea, and viruses have been revived after months of exposure to the cold, dry microgravity of the vacuum. In some cases, it's after 6 years. Even the tardigrade, everyone's favourite extremophilic multicellular teddy bear, can revive after exposure to space. The key is cryptobiosis. Many life forms can enter or produce a hibernating form that's incredibly resistant to adverse conditions. In particular, life forms that can survive extreme dryness, and hydrobiotic life forms do especially well. That includes certain reproductive spores, especially of fungi, but also critters can enter an anhydrobiotic state. They dry out, shrivel up, and wait out the bad conditions. Tardigrades are an amazing example of this, but the real champions are endospores. This is a hibernation state that many bacteria enter when deprived of the needful conditions for life. They generate a protective wall, shrink down, stabilize their DNA, and essentially shut off all metabolism. They don't need water, air, or nutrients, and are remarkably resistant to radiation damage or DNA decay. Bacterial endospores have been rejuvenated after up to 6 years exposure to the cold and vacuum of space. There are reports of viable endospores found on Earth and dated to millions of years, perhaps even a couple of 100 million years, plenty long enough to make an interstellar journey. The real challenge is radiation. Solar ultraviolet radiation in space can reach 100 million times the UV intensity of sea level. This will typically completely destroy any unprotected microbe in a fraction of a second. DNA, molecular machinery, and cell walls are shredded by ultraviolet light. Tardigrades and bacterial spores are somewhat resistant, the latter if they are in layered colonies. Photosynthetic cells, like cyanobacteria and lichens, can also survive direct sunlight in low Earth orbit, briefly. Mortality is still high in all of these. Lichens seem to do the best, with cells surviving up to several months of exposure, but probably not for years. A star's intense UV radiation probably rules out radiopanspermia. Only the tiniest microbes, probably bacterial spores, are light enough to be accelerated by a star's light, and those things are likely destroyed before they can get far enough from their home star. Anyway, even far from the intense UV radiation of a star, interstellar space is thick with energetic cosmic rays, near light-speed atomic nuclei, as well as X-rays and gamma rays. Endospores are somewhat resistant to cosmic rays, but there is a limit. The only true protection is a thick wall of solid material. Once again, we're back to impact ejector and lithopanspermia. Microbes buried deep enough in rock are entirely safe from UV and safe from cosmic rays if deep enough. Endoliths, natural rock-dwelling organisms, have representatives in all domains of the tree of life. They are often extremophiles, and their resilience often translates to the conditions of space. They also have exceptionally low metabolisms, with some having reproduction rates of decades to centuries, or perhaps even millions of years. There are endolithic bacteria, viruses and fungi dug out from deep beneath the ocean floor that appear to be a couple 100 million years old. If anything can travel between the stars, it's these guys. Okay, to review. Many microbial life forms can survive the journey into and out of space. Endoliths can survive long space journeys buried in rock. But can they really make it to another planet? And is it ever likely to happen? I mean, statistically. Let's start with the easy, journey within a solar system, like Mars to Earth. The minimum travel time for a Martian impact ejector to get to Earth is something like 6 months, although it's more likely to take years or centuries given the random nature of the journey. Those timescales are totally reasonable for the more hardy Earth microbes. Travelling between solar systems is a whole different game. First, the rock has to escape not just from the planet's gravitational field, but its star's field also. To get a microbe from the surface of the Earth to interstellar space requires a launch velocity around 4 times what is needed to just escape the Earth. That rock would endure a commensurately higher acceleration to attain that speed, with all the pressure and temperature pain that went with it. Once an infested rock makes it out of the solar system, it has a very long, very boring journey ahead. To get to the nearest stars, a rock travelling at the Sun's galactic orbital speed of 30 kilometers per second would take several tens of thousands of years. But real panspermia expeditions likely take much longer. There's only a tiny chance that an interstellar rock will be caught in the gravitational field of any given star that it passes. Take Oumuamua, for example, the asteroid that zipped through our solar system in 2017. It's going to escape our solar system, and this was probably the closest encounter it had for hundreds of millions of years. Some life forms may be able to hibernate that long, but at this point the issue is just frequency of impacts. Is it at all likely that a microbe-bearing rock from another star system hit the Earth in the short time it took life to take hold? Well, it depends on the abundance of life in the galaxy, but it seems dubious. One interesting alternative possibility is that life-bearing rocks aren't so often captured by planetary systems, but rather by the giant disks of dust and gas that precede the formation of planets, so-called protoplanetary disks. These could act like gigantic nets to capture, break apart, and disperse the seeds of life before a solar system even forms. Star-faring microbes could then remain in hibernation until planets coalesce from the protoplanetary disk, and one of these life-bearing rocks slams into a newly habitable world. Perhaps the most convincing argument against panspermia is that if the dormant seeds of life are so common throughout the galaxy, why haven't many of the 40 billion Earth-like planets produced technological civilizations far in advance of us? And speaking of aliens, a fun version of this idea is directed panspermia, in which the seeds of life are sent out deliberately to engineer life across the galaxy. That would actually be pretty easy for a moderately advanced civilization. But aliens aside, panspermia is a plausible but by no means accepted explanation for the origin of life on Earth. If it's true, then you, me, and everyone you know is an alien, a genetic immigrant from another world, perhaps with many cousins scattered across the galactic reaches of space-time. Before we get to comments, I am very pleased to announce that today's episode is brought to you by our brand new Space-Time merch store. We have all new nerdtastic t-shirts, mugs, hats, posters, and even a baby onesie. We'll be updating the store with even more merch in coming weeks, so make sure you check out pbsspacetime.com. In the last episode, we talked about the interstellar space rock Oumuamua, and the proposition by some astronomers that it may be an alien light sail. I laid out the case why this is very unlikely, And I asked you guys what you thought about the outweighted attention the media gives to these sorts of fringe ideas, regardless of their connection to reality. Is it harmful, or is any public exposure to science good? It seems that you did think about it, and quite hard. Justin O'Brien places the responsibility on the media, stating, "The problem is the rampant lack of journalistic integrity. That problem exists wherever a journalist is looking for fame and its trappings, and when a media is slave to advertiser demands." Well, this is definitely a factor when both the media outlet and the writer live or die by that month's clicks. It's easier to lose sight of old-fashioned journalism, or to make the necessary sacrifices to pay the rent. Hard to say whose fault that is. Advertisers, editors, journalists, mindless market forces, or the viewer for insisting on free content, which brings us back to advertisers. Geshtu puts it well, and I quote, "When the media says Harvard scientist says X, this is received effectively as a pronouncement of truth from scientists. When it is inevitably proven false, or the predicted thing doesn't eventuate, the public naturally learns not to trust in science as a whole, even casting doubt on all established science as well." Ian Oxenham made similar points, also adding that it's harmful if scientists or communicators do not qualify their fringe ideas with notes of caution. Otherwise, it gives the public a distorted view of how science works. And a related point. Steve Zara says that exaggerations and hype are harmful because they encourage excitement about the wrong things. Sam Winfield agrees, saying that hype over nothing leads directly to disinterest. They are crying wolf. All good points. If the press only emphasizes the most outlandish interpretations, do we eventually get bored by the real universe? Give kids too much candy and they won't eat their vegetables. In this case, Oumuamua is totally amazing as our first natural interstellar visitor, and the glory belongs to those who discovered and unlocked its real properties. Seems a bit cheap for someone to come swooping in and shout aliens every time something inexplicable is observed. And we have at least one counterpoint. Mark Gebel says that no, it's probably not harmful, at least in this case, as long as we have people to bring rationality to the dreamers and the skeptics alike. Well, it's a proud duty we have here at PBS Spacetime, squashing dreams and killing the buzz since 2015. Heartbreak One changes the subject, pointing out that if aliens were to land on PBS studios, we would do a lot of biological testing and determine that most probably it isn't aliens. Wait, are you disparaging our ability to biologically test aliens? Or are you saying we'd lie about it if we found out that there were aliens? I assure you, I will be the first on the alien bandwagon when the evidence is clear. So, you know how to be sure it's aliens? No fun buzzkill skeptics like us will be saying it too. Although, a few of you point out that denying that Oumuamua is aliens is just what aliens would say. Ergo, we are aliens. Well, to deny that would make me even more of an alien, so I guess you got me.